Yeah. It's about tool center point calibration of robots. So this is the problem in industry, for example. Tool center point, or TCP, describes a useful point for the robot. So for example, we have the welding gun on the robot, the tip of the welding gun, for example. So this is a useful point for the robot operator, so we can program with the TCP according to the part, for example, that he wants to manipulate. And so we're talking about homogeneous transformation matrices. For example, between the robot plates. What I'm interested in this work is so by the robot kinematics of the robot, for example. So every joint of the robot has a rotation angle, and this transformation metric is the combination of all the joints, for example. So I'm interested in this one. This is the standard way for TCP calibration. So this is a manual TCP calibration. So the robot has to be that tip, for example, and the robot operator moves the desired TCP to the stationary tip, for example. And he does this in the way that we get 3 different robot pulses, for example. And therefore, yes. So this transformation matrix is not completed. So we only have vector, but we cannot say anything about the rotation matrix, for example. And also the manual process leads to errors. So this is what I come up with to solve this problem. I use a 3D sensor over here, which has a coordinate system S, and the 3D sensor estimates the pose of this tool, for example. So we have a test tool attached to the robot, and in the point cloud of the sensor, we look for the CAD model of this tool tip, for example. So we get this transformation matrix from the sensor to some C1. C1 is in this example the TCP position, and therefore we get this transformation matrix. But we are interested in this transformation matrix, so from flange to C1. And by chaining the transformation matrices, we can get this transformation matrix by going this way. So get FTS, and from there, STC1, for example. And then we are at this equation, so we get FTC1, for example. So the problem splits into getting the translation vector and also the rotation matrix. So let's look at the translation vector. So as we also saw in the standard way of calibrating the TCP, for example, we move the robot in 3 different orientations in the robot flange coordinate system. So we rotate the robot around the flange coordinate system. Therefore, we get 3 points. P prime, for example, is always the same point because we rotate around this coordinate system. So with these 3 equations, we can equalize all the 3 equations and get to this equation. And we can write this as a matrix formulation. So we get a system of linear equations, and we have 3 unknowns. So this is the translation vector that we are looking for. And we have 3 equations. So it is not overall determined, so it works for us. And the next thing is the rotation matrix. So what we are doing now is we move the robot in 2 additional points. So one point is in the XF direction, so the flange coordinate system. Then we detect C1 again, so TCP, and then we move the robot also in the Y direction of the flash coordinate system, as shown in the picture. Because of measurement uncertainties, we also need to orthogonalizate YF into Y prime F, as shown here with the Gram-Schmidt process. After that, we can build a rotation matrix. So this is what we're trying to get as TF, for example. This is this transformation matrix, which consists of SRF. So that's the rotation matrix that we want. And we can build this rotation matrix up with the unit vectors. So these are the normalized vectors XF, Y prime F, and ZF is constructed by the cross product. And also, as we saw with the transformation matrices, we can also chain the rotation matrices and get to this equation down here. So this is what we want from flange to C1. So from here to here, we want the rotation behavior between that. And therefore, we use that rotation matrix that we just built and calculate it with this equation. So we also did real-world experiments with KUKA KR10 articulated robot arm. We used a stereo vision camera with depth accuracy of 0.11 millimeters and a pixel resolution of 0.22 millimeters. And we also did a reference measurement of the TCP. So we had a ground truth of everything with a coordinate measurement machine. And these are the results. So this is only the distance error, so only positional accuracy. In the slide after that, we see the rotational errors. 0 line is our reference measurement. So this is the ground truth that we use in our measurements. And we see X in blue, Y, red, Z in blue. We conducted 10 measurements with the same robot poses. And we split it into X, Y, and Z position values. So the dashed lines show the mean errors, and we get an error between minus 0.8 and 1.3 millimeters. The error in the X and Y direction is much smaller than the Z directions, as we see here. The green one is much higher. Here we see the rotational errors. So we did the experiments exactly the same as the positional error. And we got an error between minus 0.6 degrees and plus 0.8 degrees. And also the same behavior, so XY error is much smaller than the Z direction. So this leads us to the discussions. Why is the Z error much higher? So the error in X and Y direction actually corresponds quite good to the measurement uncertainty or the inaccuracy of the 3D sensor, which had an inaccuracy of 0.22 millimeters, and the error in Z direction is obviously higher. You also see the standard deviation for Y is quite big, but we have to investigate that further. So this paper was more in, is the method working? So yeah, you see it is working, but there has to be some improvement in the future to get a higher accuracy. So I proposed a new method for TCP calibration. We got the translation vector, we got the rotation matrix. So the translation matrix is completed by now. Because we use a 3D sensor for the pose estimation of the tool, we don't need any manual calibration from now on. We successfully tested it in real-world experiments, as I showed you, and the results show a good accuracy, but it has to be improved. So also the poses that the robot uses for determination of the rotation matrix, for example, this can also be investigated if different robot poses get a better accuracy, for example. Also, the time saving should be investigated in the future. So in relationship to the standard method.